So today we're going to talk about an engine that is a pretty common engine. A lot of people like it, a lot of people use it. It's the Nissan KA24. Now this is a pretty interesting engine. This engine has a lot of history with Nissan. It's basically a derivative of a Austin from those old pre-war Austin little mini cars that were made in England. Nissan actually knocked off some of these and then later actually built some Austin products under license. And the basic architecture of the KA is a derivative of that, because the Austin engine went on to become the Nissan L series, which was a performance version of the Austin basic architecture with the overhead cam, and then the KA actually built on that. So you're looking at an engine that has a lot of history, and this is the final evolution before Nissan quit supporting this kind of platform. You know, this engine probably doesn't get much respect because, you know, a few years ago, everybody was ripping these out of their 240SXs and doing SR swaps and things like that. You know, this engine, people used to throw away, but now it's been kind of rediscovered as a actual pretty good engine for moderate performance. It has a cast iron block, which is nice and stiff and strong, and it has a full bottom end girdle here where all the main caps are tied into this unitized structure that gives the bottom end stiffness. It has a forged crank and a lot of stuff that makes it pretty strong. One thing, this engine does not like revs though. You can run some boost, you can run it pretty good naturally aspirated, but don't rev it too high. Like if you try to rev these things to like 8 grand, it has a pretty long stroke, and there's harmonics going on that can even cause the block to crack and fail. Usually the block fails right where the main caps bolt to the block structure. So to avoid those harmonics, you don't want to rev it past maybe 7,700 RPM. You follow that simple rule, this thing can take a lot of power and abuse. It's kind of a good engine for beginning drifters. It makes a lot of torque. It's pretty reliable. It can take a lot of abuse as long as you don't rev it too high. And actually that's where this engine came from. One of our customers has like a fun drift car. He takes up to drift days. He doesn't compete or anything. And it's in a S14, and it served him well, but I think he finally wore it out. So he brought it here for us to refresh it. He actually wanted us to rebuild it in stock configuration because he got many years of service out of that, and he was on the budget. He didn't want us to put too much money into his beater drift car. But you know, we did a little bit better than stock. A lot of it is because the parts for these are starting to get a little hard to get. Like Nissan is not supporting this engine too much, so you have to rely on the aftermarket. Even things like the gaskets and the seals. Nissan does not stock a overhaul gasket set anymore. You could still get all the seals and stuff, but they have to all be ordered individually, and that's kind of a pain. But Nissan still has seals and some of the gaskets, but no more easy to get overhaul gasket set. Because of this difficulty in getting parts, we put together using some aftermarket parts. But what we did here is the basis of a pretty solid performance K motor too. We kind of did it to please the customer. Mostly stock spec, but you could easily turn this into a higher performance version. Let me show you how. The first thing we did is we replaced the stock rods with Manley rods. These Manley rods are a really good value. I really like them. They're H-beam construction. I tend to favor H-beams because they put extra stiffness in this direction, and that's the direction that rods are pretty much stressed, you know, in the direction of the thrust. So you have the beam and all the stiffness there, and you don't have any of the excessive weight in the middle. Now these Manley rods are made out of 4340 chromoly steel. 4340 is a little bit stronger of an alloy than like 4130 chromoly, which is a common chromoly alloy. It has a little bit more nickel and more chromium to give it some more toughness. And toughness is good because it kind of helps the ability to take multiple impact loads and repeated cyclic stress. That's why 4340 is good for cranks, rods, gears, transmission shafts, axles, that kind of stuff. The 4340 is forged into a near net shaped blank before the final machining. So what they do is get a piece of 4340, coam it under tremendous pressure with a forging machine with a die that gives you pretty close to this shape. What that does is it aligns the grain structure of the metal in the direction of the stress and in the shape of the rod. So the grain flows around the big end, goes straight here and around the small end. Think of it as the grain in wood. If you ever mess around with wood, when you try to go with the grain, the wood is really flexy and tough. But then if you do wood, bend it against the grain, it snaps. So forging aligns the grain in the metal in the right direction, really improves strength. After that, the rod is CNC machined into this shape. This gets it to the final dimension very accurately and removes any excess weight. Then the big end is finished and drilled and tapped for the bolts and stuff. After all the machining, the rod is solution heat treated. So this brings it up to the solution heat treating temperature. That way all the alloy and constituents get evenly distributed in the rod. Then it gets quenched. This increases its tensile strength. Finally, the rod is shot peened. Shot peening, they bombard the rod with really hard steel shot at high velocity. It's what gives it this pebbly finish. Now, shot peening is pretty significant. It improves the fatigue strength of the rod by over 100%. The steel shot refines the grain structure on the surface of the rod, so the grain gets smaller. So it's kind of like microforging and putting a microforged skin over the entire part. Now this hard skin is also really tough, and it's really hard for a fatigue crack to propagate in there. So this can take probably at least 100% more cycles for failure. These steps make sure that when you get a Manley rod, it's tough, strong, dimensionally stable, a good part, and somehow Manley makes it at a good competitive price. The rod on the small end has pin oil holes right here at the base. You look at a lot of rods, they put the pin oiler right on the top. Now, what's bad about that is when it's on the top, you're actually drilling a hole in the weakest part of the rod that's the most highly stressed. So a top hole can lead to like small end failure. When you drill two smaller oiling holes on the side, there's a lot more beef, and it's kind of reinforced with the ribs of the beam. The rod is also has pretty good bolts. These are ARP 2000 bolts. They're kind of the industry standard for performance rod bolts. It's not an exotic alloy that's like 200,000 KSI for instance, but these are quite a bit stronger than stock and more than enough to handle anything that you could do reliably in a KA motor. But overall, I mean, I have a hard time seeing how they can make this rod for such a good price. I mean, I would run this thing in just about anything. And if you have a really high output motor that turbo, a lot of boost, they actually have upgraded rod bolts. They call them tough bolts, and that is what you need to go to really extreme power. But anything that you can safely do with a KA motor, the ARP 2000 bolts are perfectly fine. So for the block, we align board it to make sure everything's nice and straight and we get good crush on the main bearings. This is just good procedure anytime you rebuild a motor. We used all brand new Nissan bolts. Nissan bolts are torque to yield, so it's not good to reuse them too much. We're also running a stock crank. This is the crank that came on the engine. This is a forged crank. It's really darn strong. As long as you don't rev it too high, it can take like good turbo boost and it can take a lot of abuse. To prep the crank, we magnafluxed it to check for cracks. Then we polished the journals, micro-polished them, and we sent it. A lot of times we could, with an engine that's going to be a performance motor, we'll crowd treat the block, crowd treat the crank, and then use WPC treatment. But this is an economy motor that's basically pretty stock. The guy just wants it for fun drifting. It's not going to be that stressed, and budget was important. So we didn't go too ham on the bottom end, just a good solid basic rebuild. For the main bearings, we use Clevite 77 bearings. Now these are a heavy duty tri-metal bearing. The tri-metal bearing has like a hard underlay with a lot of copper and tin in it. This gives it good load bearing capability, and then it has thinner layers on top that help your embeddability and stuff. Embeddability is the ability to like have a little piece of dirt embed in there and not like harm anything. If you have a really hard bearing, a piece of dirt gets in there and it'll just grind the hell out of everything. But if you have a bearing with some embeddability, that little particle can get sucked up by the bearing and it's fine. So the Clevite bearing is a good combination of load bearing capability and embeddability, and we like using these a lot, especially like an engine like this where there's not too many applications. You have to kind of take what you can get, and this is a high performance bearing that fits in this motor. For rod bearings, we used ACL. ACL bearings are a high performance bearing. They're used in like NASCAR, drag racing. It's a pretty hard bearing, good load bearing capacity, and they make it for the K24, so that's what we got on the rods. Let me flip this thing around so you can see what we did on the top end. So let's look at what we're doing to the other side of the engine. First off, we're using one of our favorite pistons, the JE FSR. The FSR is one of JE's more high-end pistons, and they happen to make a shelf version for the K24. Since our customer wanted to do like a quick, inexpensive build, we tried to go shelf parts as much as possible. I really like this guy because it has a lot of features from racing, but it also has some things to make it really streetable. The first thing is it has an asymmetrical skirt design. What that means is the thrust side of the skirt, that's the loaded side, is a lot bigger, so it spreads out the load. On the non-thrust side, it's a lot smaller, so you have less weight and less friction from skirt contact. It also has JE's really good cam shape. Now the cam shape is, the piston isn't exactly like a cylinder. The piston's kind of like in other dimensions, like it kind of is shaped like a barrel, I guess, and this kind of helps the piston not be noisy. So instead of the whole piston like slapping it against the cylinder wall, it kind of rocks in. And that makes a big difference in how quiet the piston is, and it also reduces cylinder wall wear when you do it right. JE has a lot of experience in cam shapes. They have different cam shapes for different applications. Their advanced cam shape actually makes this piston more streetable because this piston is a tough 2618 alloy. This is a low silicone alloy that's really tough and ductile. The disadvantage of 2618 is that it has a lot of thermal expansion, so typically you got to run a bigger piston to wall clearance, and big piston to wall clearance often leads to piston slap and making knocking noises. But JE's skirt design is pretty advanced, so you can run a fairly tight piston to wall clearance with this piston. And since the cam is well figured out, this piston is remarkably quiet considering it's a 2618. Another reason why we really like these. The FSR has a bunch of cool features too that are pretty race oriented. The first thing, it's a strut type piston. Strut pistons, the skirt is like cut away except for the friction surfaces. You've probably seen other pistons where the piston's like a full skirt and there's a lot of contact area and it's a lot of weight and heavy. And you've probably seen slipper skirt pistons like from full race motors like drag cars and things like that. Well, this FSR is a strut piston. It's almost like a slipper skirt. You see how everything is really minimalistic and pared away. But then you see these struts here that support the pin boss. So you can couple the dome of the piston and all the stress into the pin boss, so you're not sacrificing any strength, but you're getting away with eliminating a lot of weight without having the weakness. You can also see how it's undercrown milled, so any excess material is eliminated. So the FSR is strong and light. You want your piston to be light because less reciprocating weight is easier on your rod and crank. It also makes the engine more responsive and more freely revving. So it's win-win. Get rid of weight, not sacrifice strength, and not have piston slap. Other cool features is the FSR has coated skirts. We like to coat our skirts often and we have to send them out, but now you don't have to go through the expense of sending your piston out. JE coats the skirts for you. The piston pin is a high-strength steel pin. It's moderate wall thickness. You know, if you wanted to have killer boost, you'd probably want to get a thicker pin, but in the context of this engine where you don't want to go too crazy on the KA engine, this pin is fine. There's a pressure equalization groove in between the top and bottom compression ring. This helps the second ring seal better, particularly at high RPM. It gives like some blow-by gas, like a little reservoir to accumulate, so the backside of the number 2 ring gets more consistent pressure and seals better. The FSR piston has a state-of-the-art ring package. Now these are low tension rings. They're really narrow. They reduce friction, but they're still pretty durable. Like the number 1 compression ring has a plasma sprayed hard metal face for wear. The number 2 ring is a iron ring, but it's a Napier profile. The Napier ring has a pointy hook in there. That pointy hook is a high contact load area. It kind of conforms to the cylinder wall and breaks into the cylinder. This gives you fast break-in, good leak down, and the hook actually kind of flattens out and wears really long after that initial break-in. The oil ring is also a thin oil ring with 2 thin rails. It's really low tension, but it also does a pretty good job of removing the oil from the cylinder walls. There's a lot of drain back holes to help get rid of the scraped off oil. So these are really good rings, and they're going to last a long time and have low friction and seal really well. All the things you want a ring to do. Now the shelf pistons for the K24 are 9-to-1 compression. Now this is pretty good for a turbo motor, but it's kind of low for a stock rebuild and a naturally aspirated motor. But we wanted to use the shelf piston. The customer didn't want to pop for a custom piston, but like all's not lost. We kind of did some things to compensate for it. The first thing we did is this block had blown the head gasket and probably sat for years. So the deck surface was really rusty and pitted, and the cylinder walls were all rusty and pitted. So when we cleaned up the block, we precision machined it very fine, so it's really smooth. We use a low speed feed. We had to remove quite a bit from the deck, so this helps increase the compression. The other thing we did is the cylinder head had really bad electrolysis from having just basically water sit around for such a long time. When you get aluminum head and an iron block with water, basically you get a battery, and the aluminum sacrifices itself to the iron. So the aluminum head was really badly pitted. Normally we would have just trashed it, but these engines are really hard to come by. We couldn't find any of them in the junkyards or anything, so we had to fix the head. We welded it up, and then we milled the heck out of it. We took probably about 1/2 millimeter out from the deck surface. So we took maybe 1/4 millimeter from the deck here, 1/2 millimeter from the cylinder head, and we also went to a Tomei 0.6 millimeter head gasket, which is really thin. So the combination of all these brought the engine back to the stock compression ratio of 9.5. Now, if we're going to build your motor to whatever you want it to do, we can order a custom piston with a higher dome if you wanted to go high compression naturally aspirated. Or if you're going to build a turbo motor, we'd probably just use the Shelf JE piston and you'd be good to go. Some of the other tricks we did is we machined the bores with a torque plate. The torque plate is a big steel plate that simulates the load of the cylinder head on the block. When you bolt the head to a block, it usually distorts the bore. So if you machine the bore with no head and no torque plate and make it perfectly round, that's good. But when you assemble the engine and bolt the head on, the bore will distort. Then your engine will take a really long time to break in. It'll always have blow-by, and it won't last so long. So one of the extra steps we take on every motor is we use the torque plate. Now, a lot of companies don't have the torque plates for these import motors, but we take care to use on everything we do. Like I said before, this engine was neglected and sat with water in it for a few years. The rust pitted the cylinder walls, so we had to bore the engine out. Often these KA24s with the tough iron bore don't have much bore wear, so a lot of times you just give it a quick hone, put the piston in, and you're good to go. But this was so rusted, we had to bore it a 1/2 millimeter oversize. When you bore the motor and have it honed, one of the cool steps that we also do is we use a plateau hone on the final hone finish. Now, plateau hone uses like a cork bonded stone. So it's like a piece of cork with some really fine abrasive in it. And what that does is it knocks the pointy peaks off of the hone crosshatch finish. When you do the plateau honing, the bore gets really smooth. Like you can't even feel the honing crosshatching. It's still there, but you just knock the points off. So when you plateau hone, you get a lot less friction. Your engine breaks in quickly, and there's a lot less initial wear on the initial break-in. So overall, it affects the overall life of the engine, breaks in faster, provides a nicer, lower friction bore finish, and it's a little extra step that we always do on all our motors, even a straightforward econo build like this. That about covers the bottom end. This was an econo build, but depending on what piston you put in, I mean, this will handle anything from a pretty nice high compression NA build to a turbo. And it's a solid building block to do a lot of cool things, and it's about what we would do for almost any motor. So let's look to see what we did with the cylinder head. So our customer didn't want to go off too much on the cylinder head. He just basically wanted a nice, solid, long-running head. So what we basically did is got the head, cleaned and inspected it for cracks, and then basically put it back together. This head was heavily damaged by electrolysis, and it had really bad pitting in the combustion chambers and on the deck surface, so we had to send it out and get repaired. So basically what they did is they TIG welded, or they ground away all the electrolysis with a die grinder, and then they TIG welded the surfaces up, and then they remilled the head to get rid of the weld beads, make everything flat, and used a die grinder and a flap wheel to kind of clean up the combustion chambers where they had the weld. It's a really good job. Like, you can't even tell this thing was even welded on, really, and pretty much restored the head. The only bad thing is it had to cut the deck surface some. But in the case of what we have going on here, it was actually a good deal because it helped us get the compression ratio back. This head was really pretty heavily worn. Like, the valve guides are really loose. So we knocked out the stock Nissan valve guides and replaced them with silicone bronze. We checked the valve stem to guide clearance. They're nice and tight so this thing won't burn oil. And we did a good 3-angle valve job. 3-angle valve job is where you cut your 45 seating angle, and you have a 30-degree top cut and a 70-degree throat cut, which helps the flow make that turn into the exhaust port and out of the intake port into the combustion chamber. Just cutting those angles actually picks up quite a bit of power usually. So we did that on this. Nothing fancy, just a nice straightforward 3-angle valve job. Now, let's say you wanted to do some performance stuff. We can easily accommodate you. For cams, this engine has stock cams and valve springs, but if you wanted to go hotter, we usually use Jim Wolf Technology cams. So they have several grinds depending on what you do. For a turbo motor, we'd use a mild cam. For NA, we'd use a bigger cam, but generally we feel Jim Wolf makes the best cams and springs and everything for this combination. We could WPC the cams and the buckets and the springs, longer life, less friction. We didn't do it here. The customer wasn't really interested in that. There's other things like we could port the head, like on the exhaust port here. We could probably narrow down the port splitter because it's kind of fat and chunky and there's not much area coming out of the bowl into the port itself. So could probably benefit from narrowing down the port splitter. The intake side is actually a pretty good shape. Decent shape. Probably narrow down the port splitter again and maybe take some off the short side radius on both the intake and exhaust and get some more flow, more power, but that's not the context of what was done here. Just wanted a nice, solid running, long lasting, close to stock motor. A cool trick that we do on the valve trains on these motors is we use a VQ select fit cam follower. Now the stock cam follower is a kind of a shell, and it uses a shim on top of it to get the valve clearance. Now what's bad about this is if you have a big cam or if you rev really high, the lobe of the cam can flip that shim out like a tiddlywink, and that is not good. Usually bad things happen when that happens. Also, if you hit the rev limiter too hard, that could happen. So when we replace it with the VQ follower, these are available in a whole bunch of different sizes, so you don't have the shim, so there's nothing to flip out, and it's a lot lighter and more stable under high RPMs. For this motor, the customer just wanted to run stock valves, so that's what we did. There's aftermarket valves available, like if you're building a turbo engine, we'd probably use an Inconel exhaust. We could use a higher flow stainless. It's whatever you want, but basically all the tricks are the same as what we did on this motor. It's just expanding on what we did a little bit. This motor is a solid basis that could support other mods later too. So you can see that even this basic K build, you could easily expand it to get more power. Now, it's not like a 4G63 or a Honda K motor where you can get tons and tons of power, but you could probably make up to 500 horsepower with a turbo and, probably about 200 horsepower NA with a nice fat power band with a K if you don't go too crazy. So there you have it. Things you could do with the Nissan KA motor. It's not too bad. And it's been ignored way too long. If you like this content and you want to see more, be sure and hit the subscribe button and go to MotoIQ.com. Check out all our articles. We got a lot of tech and all kinds of subjects, and I'm sure you're going to like it. So until next time, we'll probably be looking at more motors. I'm not sure what, but we have a Honda K build and a Chevy LS coming up. So we'll see you later.